The very first thing that we want to do is to factor that denominator. So I've got x plus 2 in my numerator, and that denominator factors into x minus 2, x minus 1, and of course we've got our dx. This allows me to set up my partial fraction decomposition. Now I don't feel like writing that out, so I'm going to write partial fraction decomposition. I'm going to go ahead and just pull this rational expression out of our integral, and let's go ahead and work with that. Now, because I've got two factors in my denominator, I'm going to go ahead and rewrite this. Let me put this over here on the left, x minus 2, x minus 1. I'm going to write this as the sum of two rational expressions with each factor as a denominator. Now, it's important that these are proper fractions. I want the degree in my numerator to be smaller than the degree in my denominator. The degree in my denominator in both of these is degree 1, so I need my numerator to be degree 0. That means that I want a constant and a constant in both of those. I'm going to take a shortcut here and just compare my numerator next. So comparing my numerators, I've got an x plus 2 on the left, and on the right, I'm just going to multiply by what each of our fractions is missing for that common denominator. It's kind of like cross multiplying, but I'm multiplying by the missing factor. A is missing x minus 1 for that common denominator, and B is missing, let me do it this way, B is missing the x minus 2. So we end up with a B parentheses x minus 2. On this one, I can use my method of zeroing out, and I'm going to start by zeroing out this factor x minus 1 by letting x equal 1. And then I'm going to go back and do something similar with a 2. Let's go ahead and start with that x equals 1. So when x is equal to 1, we have 1 plus 2 is equal to a times 1 minus 1, which is 0, plus b times 1 minus 2. So doing my math here, I get 3 is equal to a times 0, that one goes away, and I get a negative b. So that tells me that b is equal to negative 3. There's my first one. I can also zero things out by letting x be 2. That's going to zero out my b term. So by x equals 2. So when we let x equal 2, we end up with x plus 2. That's going to be 2 plus 2 is equal to a times 2 minus 1 plus b times 2 minus 2, which is equal to 0. So we end up with 4 is equal to a times 1, and a is equal to 4. So if I go back and look up at my template, I know that I can replace an a with a 4, and that b can be replaced with a negative 3. Well, let me go ahead and rewrite this, and I'm going to rewrite it inside of our integral so that it's a little neater than what I've got there. So this gives me my integral now in a form that I can integrate. So I have 4, and that was over the x minus 2. So I've got 4 over x minus 2. And then b is negative 3. So negative 3 over the x minus 1. And this is all dx. Both of these now are really easy to integrate. I know that if I've got something in the form of 1 over x plus or minus something dx, this turns out to be a natural log of x plus or minus whatever that value is, and then of course a plus c on the end. So I can integrate both of these separately. I'm going to pull that 4 out in front, and then let's go ahead and take care of the over x minus 2. That's going to become the natural log of absolute value x minus 2. And then I've got my minus and my 3, and I need to do the over x minus 1. This is going to be the natural log of absolute value x minus 1, and all I've got left is a plus c. But what happens when we've got degree 2's in our denominators? Now I again want to start by factoring that denominator, and it has 3 terms, so it should factor, and it does, into 2 binomials. To get to the x to the 4th, it's going to be an x squared times an x squared. To get to that 2 on the end, this is a nice one, right? It's going to be a 2 times a 1, and everything's positive, so I get a plus, and I've got my dx there. Now, both of these denominators are irreducible quadratics. That means that I can't factor them any further over the integers. So I need to set up my template a little bit differently. I'm going to go ahead and take that rational expression out of my integrand for now. X squared plus 1 is equal to, and I know that I need to set this up as a sum of two rational expressions, x squared plus 1. Now, both of these are degree 2, and in order to make these proper rational expressions, I need my numerators to be degree 1. Well, degree 1 would be linear, like y equals mx plus b, right? That would be linear or degree 1. But in order to put this together in terms of my template, I'm going to use those capital letters for our coefficients. So that first linear numerator is going to be an ax plus b, and that second linear numerator is going to be a cx plus d. Now I'm going to go ahead and do the next step with that same shortcut that I saw before, comparing just my numerators. So comparing just my numerators, I have a 1 on the left-hand side, and on the right-hand side, let's go ahead and start by multiplying ax plus b by its missing factor from the denominator. It's missing that x squared plus 1. So we have ax plus b times x squared plus 1. Similarly, that cx plus d is missing the other factor x squared plus 2. So then I've got plus parentheses cx plus d times x squared plus 2. Now in this one, I cannot use that zeroing out method. I'm still going to show you a shortcut though, but we do need to expand what we've got there on that right-hand side first. So I'm going to move this up so I've got a little more room to work, and I have 1 is equal to, I'm going to just start multiplying things through. And as I'm multiplying things through to keep things in order, I'm going to do it instead of FOIL, first, outer, inner, last. Let's do it in descending order. That means that I want to start here with ax times x squared. So that gives me ax cubed. The next one is going to be a bx squared, so plus bx squared. And then we've got an x term that's going to be ax times 1, so plus ax. And then on the end we have a plus b. Doing something very similar to the next one, I'm going to go ahead and start with my cx times x squared. Let's line our like terms up. So this is going to give me a cx cubed. And then for those squared terms, I get a dx squared, so plus dx squared. Looking for that x term, that's going to be a cx times 2, so plus 2cx. And then finally on the end, I've got d times 2, so plus 2d. And my method is called comparing coefficients. I know that I need the left-hand side, the number 1, to equal the right-hand side. So as I compare my coefficients, I'm going to compare my coefficients in order. I've got coefficients for x cubed, coefficients for x squared, coefficients for x terms, and coefficients for constant terms. Let's go ahead and start off with our x cubed terms first. Our x cubed terms are here. I'm going to pick up the coefficients only, and you'll notice on the left-hand side there are 0 x cubed. So I can write that 0 x cubed on the left is equal to an a plus a c on the right. Next, we're going to move to x squared. So for x squared, we have b plus d, but again, we've got 0 of these on the left. So I have 0 is equal to b plus d. Next, we want to do our x's. And so our x's, I've got an ax and a 2cx. But again, 0x is on the left, so I've got a plus 2c. I am just about there. And I'm going to finally pick up a term on the left-hand side other than 0. I get a 1 there, and then a b plus 2d there. So I get 1 is equal to b plus 2d. Now you could completely break this down and work it algebraically, and you can pick up your AC equations and solve that system, and then pick up the other two equations and solve that system. But there is a much easier way, and it's going to be in your TI-84 calculator. I'm going to set this up into a matrix. Once you get the hang of this, it's going to save you so much time. My matrix is going to have 1, 2, 3, 4 rows to it, one for each equation. And those equations line up with my degrees, right? X squared, x to the first, x cubed I forgot, and then my constants. And then across the top, I'm going to put my coefficients. I've got A, B, C, D, and I'm actually going to swap these around, and I'm going to put my equal sign, and then I want the constants on the other side. Okay, so here's what that looks like. I'm going to start here with 0 equals a plus c. So 0 goes here equals 1a plus 1c. That means I've got 0 b's and 0 d's. I'm going to put a line right here. This is called an augmented matrix. I promise once you get the hang of it, it's going to save you a ton of time. Okay, next is our 0 equals b plus d. So 0 goes on the other side, and then I've got 1b and 1d, 0 for a, 0 for c. Okay, so check, check. Next is 0 equals a plus 2c. So 0 equals 1a, 0 b's, 2 c's, and 0 d's. Check. And then our last one is b plus 2d. 1 plus 2d's, 0, 0 is equal to 1. I'm going to put this right into my TI-84 graphing calculator, and I'm going to let my calculator do the hard work. We want to put this in as a matrix. To access that menu, I'm going to hit the second button followed by the matrix button, which is the x to the negative 1. So second matrix, I want to edit or input a matrix. So let's arrow over to edit and then hit enter. This wants to know the dimensions of my matrix. I've got 4 rows for the 4 equations, and if I count across there, I've got 5 columns. So this is going to be a 4 by 5 matrix. Now I'm going to put in all of my values very carefully. So I've got 1, enter, 0, enter, 1, enter, 0, enter, 0, enter. Row 2, 0, 1, 0, 1, 0. Row 3, 1, 0, 2, 0, 0. And then row 4 is 0, 1, 0, 2, and then 1. Once I've got my matrix in here, I'm ready to ask the calculator for row reduced echelon form. Here's how we do it. I want to go back to my home menu, so second followed by quit, and then into my matrix menu, so second followed by matrix. This time I want to go to the math sub menu. I'm looking for row reduced echelon form, RREF. If you arrow up, you're going to find it. So arrowing up, I find RREF is right here. Let's go ahead and hit enter. And I want to give it matrix A. That's where I put all of my information. So back to the matrix menu. So second matrix, and I do want matrix A. Let me hit enter and then enter again. Now take a look at what it is giving you. If I read each of those rows, the very first row says that 1A is equal to 0. That means that A is equal to 0. Second row tells me that 1B is equal to negative 1. So I get a coefficient there. B is equal to negative 1. The third row tells me that 1C, so I can just say C is equal to 0. And D, 1D is equal to 1. There's my other coefficient for my template. D is equal to 1. Let's go back and grab that template, and then we're going to be able to integrate. Here's our template. We know that A and C were both equal to 0, so I can get rid of those. And I want to replace B and D with the values that we found. Okay, so I've got B is equal to a -1, so -1 for B, and D is equal to a +1. Now this represents the partial fraction decomposition for our original integrand. So I can put this right inside our integral with a dx on the outside. So my antiderivatives here are not going to be natural logs, and there's no u substitution that I can do. So instead, I'm going to recognize that the integrals, the antiderivatives, are both a tan inverse. So I'm going to look at those denominators as an x squared plus an a squared. In that first fraction, if a squared is 2, that means that a is going to be the square root of 2. In the second one, a squared is 1, so a in the second one for our formula is going to be a +1. So for that first one, let's go ahead and pull the negative right out in front, and I want 1 over a. So that's going to be 1 over radical 2 tan inverse x over a, which is going to be x over radical 2. Plus, for the second one, it's going to be a tan inverse because that's just going to be 1 over 1. So tan inverse of x, and then of course our plus c. You are doing amazing. I've got another video for you here.